Hello everyone. In this video we are going to look at mobile robots, the robots that have a mechanism to move their base with respect to the environment, right? Because you know the manipulator arms that are used in factories for assembling, pick and place, and so many other tasks. They also move. They are mobile, but the base of them is attached to the ground. So these robots, the base of them does move. Okay, and you see them all around in all sorts of activities and applications these days, from the ones that go inside, let's say, a nuclear reactor that is failed, right, in Japan due to tsunami. They send it in to go and do some basically information acquisition, some reconnaissance and anything, and bring back the extent of damage, and so then the people can get in, right? You see them working for police. You see them in your house doing the vacuum job. You see them on the Mars, right? As this Mars rover going and collecting information, bringing in samples of rocks and so on. You see them in your classrooms like this Quanzer for your education. Sometimes you might even see them in museums moving around and giving some information and basically receiving people. So there are all sorts of mobile robots that you'll see. And these mobile robots have different mechanisms for moving, different locomotion mechanisms. What are they? So if you look at them, there are all sorts of different mechanisms for motion. Some of them, if you start from this bottom right, some of them move on water. So these are autonomous, basically boats. Some of them are in the air, like the drones. Some of them are completely different, like the snake robots. Some of them look like animals. Some of them look like humanoids, like the Atlas robot. Some of them, like this scorpion robot, they have several legs, right? They're hexapod and so on and so forth. So in general, as you can see, these three guys down below here, these are legged robots. Okay, so these three on the bottom left, these are legged robots. This is separate of its own. This basically snake robot, correct? That is crawling. The flying robot, the floating robot. Then we have the robots like the self-driving car that has the steering mechanism of a real car, so it uses something called the Ackermann geometry, or it's bound to or constrained to the Ackermann geometry, which means one tire rotates more than the other one when you are going on an arc, on a circle. You have the differential drive robots that have two tires that in general they can be rotated individually from each other, and based on the difference of the RPM of those two wheels, the robot can go forward, backward, can rotate, and so on. And they typically have one or two wheels that are not driven, and they are there just to stabilize the robot statically or dynamically. You can see it probably here, right? So there is like typically a wheel here, most of the time looks spherical like a ball, and it is constrained inside a chamber which cannot get out of it. It is in contact with the ground, because if any object wants to be statically stable, you need three contact points with the ground. So two of them are the driving wheels, one here, and this one, as I said, it is called the caster wheel, which is not driven. Okay, so this is called differential drive. And differential drive have the limitation that they cannot move sideways. So if at the moment you ask them to move to the left or to the right, they cannot do it immediately. What they need is they need to go on an arc to move to the left or to the right. They cannot move sideways, right? The same thing for airplanes. The fixed-wing airplanes, they cannot in the sky go immediately to the left or to the right. if they want to do that, they need to what we call bank, correct? So the airplane needs to change its angle from going straight like this to at angle like this, correct? So the airplane should look like this instead of this one, right? They do what we call the roll angle, right? And then they can bank to the left or right. But the drones don't have that problem. They have 4 separate motors that can move them in any direction. So similar to those, as I said, on the ground, these differential drives like this one, they cannot move to the left and right. We call it a holonomic and non-holonomic constraint. That I'll talk about it. The same thing about your cars. If you look at your cars, when you are in the street and there is a spot for your parking, so let's say here, these are the cars parked next to the sidewalk, and you are on the street and you come here with your car and you want to park. As you know, you cannot just sideways move on and park there, right? You have to pass it probably and then move back and try to steer and fix your position and put it there, right? So when you do the parking, that's because you cannot move sideways. Therefore, there are some other types of robots, which we call them omnidirectional, these guys. These omnidirectionals in general, they can also move sideways. Okay, they have the capability to move sideways, like this one. This is like the general omnidirectional wheel. So they have these rollers that allow them to move or slide sideways. We have these guys here, which they have the rollers at angle, and we call them the mechanism wheels. And then we have these kind of new ones that have like a ball, right? Their wheels are spherical instead of basically cylindrical. So these guys can move sideways. You can even have unicycles like this. They are not really typically used too much, but you might even see something like a unicycle that can move too. The problem with the unicycle is they are statically not stable, right? They are unstable, so you have to make sure you stabilize it. The same thing with the humanoid robot, okay? It's not statically stable. It only has 2 contact points with the ground. So controlling this type of robot that they have 1 or 2 contact points with the ground is way harder. But when we have more than 1 contact, 3 or more than 3 contact points, like this one has 6, this one has 4, although this 4 also is not quite as easy. But if you see here, I have 2 driving wheels and a caster. Here you see there are 3 of them. For this omnidirectional, many of them typically have 4, some of them have 3. But they are statically stable, so you don't need to worry about whether they fall down or not. All you care about is to steer them. Okay, so the stability of them is quite important. So these are all sorts of different mechanisms for motion as far as I know, and we see their application. Now the overall system of a mobile robot is like what? So a mobile robot typically needs to interact with the environment and perform a mission, right? It needs to do a mission. So when you give it the mission, let's say the Mars rover, right? You ask the Mars rover, hey, move on the Mars surface from this point to this point, go to some location, drill the ground, collect some sample and bring it back. So that's the mission. Go explore, collect samples, come back. So what does it know? How can it interact? How can it perform the mission? Well, first of all, in general, you might have some knowledge and database about the environment in which the robot is working, right? So you might have some pictures, some general data from the surface of the Mars, which you could get from all sorts of basically space missions that you send, unmanned missions that you send, maybe some satellites that you send that are orbiting the Mars, or any kind of information. For the self-driving car, for example, the information that we have mostly is GPS, right? That we have from several satellites around the globe. So or if it's like the robot that is going inside a failed nuclear reactor, that could be the floor plan of the building, right? So many times you have some knowledge from the environment and you need to use that as much as possible. But that's most of the time is not enough, because the environment is not most of the time statics, it's dynamics. There are objects moving in the environment, stuff are changing. If the car is driving on the road, the self-driving car, there are some road closures, local repairs, and so on, not reflected in GPS immediately. So you need to have different ways to sense the environment and interact with the environment and extract information. So you need sensors. The sensors are typically like lidars, radars, cameras, sometimes acoustic sensors. There are all sorts of sensors that we can have, right, that interact with the environment. And there are also some internal sensors which help determine the location and orientation of your robot too, like accelerometers, like gyros, like magnetic sensors, and so on and so forth, heading sensors. But these sensors that interact with the environment, as I said, they are like radar, correct? They are like lidar, which is for laser. You have to aim it really. Your cameras, all sorts of cameras, RGB cameras, LWIR cameras, RGBD, which D stands for depth. So those cameras can get pictures as well as depth, right? You have acoustic sensors and so many other things. So with those, you interact with the environment. So if you're driving on the road and you want to go from point A to point B, and GPS is telling you where to go, but all of a sudden somebody jumps in front of you in the lane or changes lane and kind of blocks your motion, you have to maneuver around it or stop or do something, or somebody jumps in front of you in the street. So your sensor will extract raw data from the environment, and then you need to extract meaningful abstract information from them and interpret them, right? So because the images that you are getting are typically what? Thousands and millions of pixels, right? If you have an image that is like 1200 by 800 pixels, right? That's just a bunch of numbers, right? It's just a big rectangle with so many points. Each one of them is called a pixel, and each one of them has a value, let's say between 0 to 255 if they are 8-bit integers, and that is your channel R. Then you have another rectangle. This one is your channel B, the blue, and then you have channel green, or green and blue. Right, so you have so many red values, so many green values, so many blue values, and right, as I said, let's say this is 12,000 pixels by 800 pixels or so. So in each direction, as you can see, you have what? 8 times 12, right? So you will get 1.6 million, if I'm not mistaken. Correct? So you have 4 zeros, and then 8 times 12, no, 96. Okay, so 96 and then 4 zeros. So about 1 million pixels. In the R, 1 million pixel in G, 1 million pixel in B, and if you have depth, then you might get something similar than that. So these are so many data values, right? These are so much of information. All you want is whether there is something in front of me here or not, right? Is there a person here in front of me that is blocking my way, or no, there is a car blocking my way, or anything for that matter. If you can extract that information, that is what you need to act based on, not all of these small pieces of information. hey, here the number is like 200, here the same pixel is 100, here it is like 50, and here maybe is 1 meter or so. Okay, so extracting information from these sensors is a job of its own, which we typically do using computer vision, machine learning, and so on. Once you get this info, then you try to update your map, right? Because your map that you get from general info, if you have such a thing, it is not complete and it is not typically completely updated. So you try to update the map, or if there is no map, you try to build a map. And at the same time, localize yourself. So if you have the GPS, most probably you can localize yourself. But once you send your robot inside the building where GPS does not work, you cannot easily localize yourself, right? So you have to use different algorithms and methods for localizing yourself. One of them, which is the base, is called odometry, which is basically a dead reckoning, counting in which direction, how far, about how much time you have moved, and try to estimate your location, but it is subjected to some problems like drift. So you have to have some complementary mechanisms to get accurate estimates of your position, and that's where your sensors like camera, LiDAR, and so on can help you to not only build a map from the environment, but also try to localize yourself. And that's where some topics like SLAM that I mentioned in one of my previous videos, simultaneous localization and mapping, comes into play. There are some topics come to play like loop closure, which is basically seeing a feature that you have already seen in the past and then updating all of your odometry calculations based on that and correcting those. Call it a batch basically fix, right? A batch correction. So these are all the topics. Each one of them is a topic of its own, and you can teach a course on each one of them. Especially this extracting information, you can teach several courses on that alone. So once you have a good map, an updated map, and you know where you are in that map, then you can execute your mission. You can go from one point to another, you can collect something, and so on and so forth. And in this path, you have to control your actuators and command them and tell them whether they are motors, they are whatever linear actuators, or so on, to do their job. Okay, so the job of mobile robots, especially the ones that are interacting too much with the environment, they are actually very hard jobs, and especially if they are completely autonomous. If they are semi-autonomous, so there is human involved, human can help with a lot of these tasks and make the job a lot easier. But for many tasks, there might not be a human. For some of them, there might be. So if you can teleoperate the robot and so help the robot maneuver around obstacles, not fall into the holes, right? And go to the correct point, collect the correct sample, and so on, that can help. So that's why, as long as we cannot get reliable localization and reliable mapping, and we cannot do it accurately, there is always a human in the loop, and we call it a semi-autonomous robot. Good. The last thing is some of the difficulties that come into play when you are trying to analyze the pose of a mobile robot and control that. And by pose here, we mean a combination of the position or location and orientation. So the most important one and the hardest one is the inaccuracy in position estimation or orientation estimation, and the hardship in it, not just inaccuracy, the hardship. The problem is when you have a mobile robot and this mobile robot is acting, if you want to know the correct orientation of each member And so you also need to know the correct position of the robot, the configuration of the robot basically. All you need is to know the angle of each member. If you know the angle of each member, because the members are rigid and the base of the robot is attached to ground, finding the location of each joint, the end effector, and so on is an extremely easy job. So all you need is, can I know the angles theta 1 and theta 2 correctly? And yes, you can do that using the encoders, right? So if your motors have encoders or position feedback, that's all you need. They can give you with a very good amount of accuracy the location of the joints, the angular or the linear position of the joints, and that's all you need. But when a mobile is moving, the base is moving, that's not an easy task. You need to have a way to properly and accurately estimate the location of the robot. And how do you do that? Well, if they are outside and you can use GPS, GPS can help you. Although, you know, GPS has its own limitations, right? GPS is not accurate to a fraction of a meter or fraction of a foot or something, right? Typically, regular GPS varies their accuracy between 3 to 10 meters, right? Many of them up to 10 meters, they can have error. And that's one thing. Now, there are some other new types of GPS called differential GPS, which can give you sub-meter accuracy, but they are very expensive and they are not freely available for regular robots. So GPS has error, right? Up to 10 meters. And if your accuracy needs to be sub-meter, below meter, then GPS has its own error, right? Because all it does is basically the position of the intersection of several spheres, where the center of the spheres are on the satellites, and the radius of the spheres is the distance that the satellites can measure from themselves to you and back. So here you typically need more than 3, typically 4, at least 4 satellites to be in your vision to get 4 spheres intersecting each other, so you can find the location of you on the Earth as well as the time and everything. And most of the time there is a lot more. Many times you have 17, 18 satellites, so you have to do at least a square problem. And that's why you're going to have some errors, right? The least square problems are never accurate. You get just the minimal error possible. So the problem is, as I said, you cannot find it even outdoor. Now, if you go indoor and the GPS is gone, that is way harder. All you need to count on, as I said, is called dead reckoning or odometry, which is basically, let's say, if this robot is moving and these tires are rotating, let's say both at the same time, the same RPM. And let's say each one of them is rotating with, let's say, 1,000 RPM. So you convert that into radians per second. You know, when they rotate the same amount, the robot goes straight. And if you know the radius of these wheels, and if they are the same, right, radius of the right, radius of the left, so if you multiply the radius by omega, that gives you velocity of the centroid of this one, and the velocity of the centroid of the robot is the average of the two. So basically this is going to be the omega times r, right? That's all it is. But what's the problem here? The problem is the slip. That's one of the main problems which I mentioned here, slipping. So sometimes your tire does rotate and your encoder records the rotation, but the problem is the robot does not do pure rolling without slipping. There is a little bit of slip here, so not all of the rotation is transformed into translation. So if the motion of the center, VC, and the RPM is, let's say, omega, and the radius is r, this VC is not going to be equal to omega r, it's going to be less than r times omega. That's slipping, right? Or sometimes it's the other way around. You're locking the brakes, right? If you have a brake, you're locking the brake. Omega goes to 0, but your tire is still moving. So your VC can be bigger than R omega, right? So in general, as long as VC is not equal to R omega, we can say there is what? There is a slipping. And it happens a lot. As long as there is not enough traction below the tires, or there is a locking in the brakes while the mechanism still moves and so on, there is slipping. The other thing that you have is backlash in the gears of the gearbox, okay? So when you have these gears in the gearbox of the motors working together, right, like this, the thing is, each tooth, when it goes in the empty space between the other teeth, there is some what? There is some space that it can move. So if you lock one wheel, the other gear can still move a little bit. That amount of motion when one of them is locked is called backlash. And that backlash is causing all sorts of nonlinearities in motion and so on. It can even causes something we call chaos. I did my master's dissertation on that, so I know. So this backlash, frictions, so many things, inaccuracy in the sensors. The sensors also have accuracy and resolution problems. Like, for example, here I said the odometry is done based on the rotations. And the rotations, these encoders, they have some resolution, right? So they can probably give you what? Let's say 1 degree accuracy, right? They cannot give you less than, depending on how many slots you have on the encoder wheel, right? If you have 360 slots, then they can give you 1 degree accuracy, 1 degree resolution, I'm sorry, right? Or there is any problem in if they go super fast, the sensor might not be, the computation of the sensor might not be, the optocoupler might not be that accurate. So the sensors are not perfect. They have problems of resolution, they have problems of accuracy and so on. So all this combined, when you do it and you do this dead reckoning, what causes it is what it causes is going to be what we call drift. So if here, let's say I ask my mobile robot to move on this square in black, right? And I try to keep moving on that square just by dead reckoning. If you look at the actual, if you have a method of actually tracking the robot, you see over time it drifts away from the actual path and separates, okay? So this drift problem is a serious problem, and it is due to all sorts of these problems that I mentioned, right? Even if you have gyros, that's the same problem. The gyros also, they give you angular velocity. And when you want to convert it into angular position, you have to numerically integrate versus time. And when you do numerical integration, you always have some error accumulation, and that is another source of error that you have. So gyros also cause errors. And then different environment and so on and so forth. So in general, tracking mobile robots, especially when GPS is not available, is not a simple task. So they try to use vision sensors, and if there are something like a landmark in the environments that you know ahead of time, like as you go around this building, maybe you know that at a specific location there is a statue over there. So whenever you reach that statue, you know your location, right? Or there is some other door here that you know, or there is some window here that you know. So if you can detect those using your sensors, especially cameras, then you can find your accurate location. And not only that, you can also look back into the estimation of the position that you had using odometry, and you can fix those estimations that had drift, and that's what we call the batch correction. Okay, in many control environments, you see all sorts of these lights, infrared lights, all sorts of other types of lights on the ceiling, on the walls, and sometimes on the robots, and that's for tracking the robot So basically, if the robot can detect, let's say, 3 of these lights, right, at least, and we know their location, you can what we call triangulate the robot using these bearing angles that you have. That's one way. Or if those systems are capable of basically they're detecting something specific on the robot, they can also triangulate down the robot to very accurate position. So this is what you see in many environments working with drones or mobile robots. They have all sorts of lights on the walls, ceilings on the robot, or sometimes there might be a beacon on the robot and some basically devices for receiving that beacon and then triangulating the robot. So that's another thing, but that typically happens in controlled environments and labs and not everywhere in indoor environments when you don't know ahead of time that you are going to do a mission like that nuclear reactor. So hopefully I told you enough of info just for knowing what a mobile robot is, how they move, how they interact with environments, some basic terminologies, and some difficulties in estimating and analyzing or controlling the position and orientation of the robots that together we call them pose. I'll see you in my next lecture when I talk about differential drive robots. Thank you.